Hi everybody, my name is Timofey, and in this video I'm gonna reproduce a talk that I've given at a conference in Gothenburg, Sweden, the Gothenburg Region OpenFoam User Group Meeting. You see the title of the talk now on the screen, WallModelled LES Simulation on Unstructured Grids. But before I dive into that, I just wanted to give it like a short background motivation to why I decided to do this video. And I have a little example open here on YouTube. So as many of you, I guess, know, there's a sort of a culture in conferences related to programming to basically record all the talks and then upload them to YouTube so that everyone can enjoy the talks even though they weren't present at the conference. So here I just have as an example the SciPy 2018 Scientific Computing Python conference. And as you can see, there's a whole playlist of basically all the talks that were given there. And I think that's very nice. And unfortunately, you know, in more classical science conferences, there isn't such a culture of uploading the talks or recording them all together. So what I thought is that, you know, I can actually do this with my own talks. Now, obviously, I can't, you know, or maybe I can, but it's a big hassle to record the live performance. But what I can do is that basically after I've given the talk, create a YouTube video using the slides that I've already prepared, and in this way basically create like a copy of the talk which I can then upload and share with everyone. Now obviously, you know, I'm not going to get 26,000 views on it, but the thing is, so for instance this talk that I'm going to reproduce today, it was given in a room with about 20 or 25 people. So that means that if only, you know, let's say 30 people or so look at the video online, that means I've more than doubled the audience of this talk. So and that I think is just quite nice. So that's pretty much the motivation here. So let's now dive into the talk itself. Let me put this on full screen here. All right, so the title again, WallModelled LES Simulation on Unstructured Grids. So as you can see, I have a Chalmers University of Technology presentation template here, and the reason for that is that I work at Chalmers as a postdoc. But the material in this talk is actually based on the work I've been doing in Uppsala University, where I've recently finished my PhD studies. Before I start, maybe just a few more words about the conference itself. So as I said, it was this Gothenburg Region User Group Meeting for OpenFoam users. And that's basically quite a small gathering that happens every year, which, you know, people that use OpenFoam in their CFD workflow one way or another. It can be both research and also there's some people from industry coming regularly. And yeah, pretty much everyone who wants can give a presentation. It's also free, the attendance to the conference. So it's a nice cozy get together. And I should say that, you know, everyone is welcome to this event, independently of whether you are in the Gothenburg region or not. It's loosely defined. There were some people from the Netherlands, for instance, and from Denmark this year. And before, I know that there were people from England, for instance. So it's really, everyone can join in. So I encourage you to do that next year if you are into OpenFoam. Okay, so let's start. So the focus of the talk is going to be, you know, the unstructured grid part. So that's really what I wanted to focus on here. But of course, I can dive into that before I actually discuss what WallModelled LES is, at least a little bit. So I'm going to give a short introduction here in the first couple of slides. And basically, the way I'm going to do this is first draw your attention to this mean velocity profile I have on the figure here. And this is a mean velocity profile from a flat plate turbulent boundary layer. And what we can do is we can divide this profile into two overlapping regions. And one of those regions is called the inner layer and the other is called the outer layer, or they also call inner region and outer region. Now these two regions are overlapping, and what we have here on the figure, this orange rectangle is actually where the two regions overlap, and that's called the overlap layer or the overlap region. And then to the right, the big yellow rectangle is the remaining of part of the outer layer. So it occupies pretty much, about 80–90% of the profile is the outer layer. And then below the overlap layer is what remains from the inner layer, the pink rectangle. And the idea of WallModelled LES is basically that we're going to resolve all the turbulent structures as in normal, what I will call wall-resolved LES here, in the outer layer, so up to this point. But we're not going to resolve the turbulent structures in the region of the inner layer below the overlap. So we're not going to resolve the turbulence in this pink rectangle. Okay, and of course, if we go for that kind of approach, then we have to introduce some special modeling to compensate for the fact that we have ignored these important turbulent scales in this pink rectangle here in the inner layer. And that is then the wall modeling. Now, since this talk is focused, or going to be focused quite a lot on grid generation, it's important to point out already now that once we said that we're only going to resolve turbulence in the outer layer, we no longer have to think about our grid in terms of plus units. Generally, when we talk about meshing a turbulent boundary layer, usually in RANS we say, we have to put our first cell center at a certain y plus, and so on and so forth. In LES, classical wall-resolved LES, we instead say, we both need the one y plus 1, let's say, for the first cell center, and we also need to take care of a delta x and a delta z plus, so in the wall parallel directions. And there are certain guidelines for which sizes and plus units are appropriate for the grid. But the whole idea here is that in the outer layer, the turbulent structures do not scale with inner length scale, so with the plus scale, but they instead scale with delta, so the outer scale. And that means that we're going to define our grid in terms of the outer scale, so basically the cell size as a fraction of this delta. Much more about that later. Before we continue with some more details of WallModelled LES, so why do we actually do that? So the whole idea is, of course, that we can save computational resources by ignoring some of the scales of our grid. And for a flat-plate turbulent boundary layer, there are estimates on how the number of cells in your grid scales with a Reynolds number. And for wall-resolved LES, you can see here that the scaling is almost a square, so Reynolds to the power of 1.85. But if we go for WallModelled LES, we get instead a linear scaling. This is of course much nicer. This means that we can afford to simulate flows at much higher Reynolds numbers, those Reynolds numbers that are closer to what we actually encounter in many industrial flows. Okay. So there are many ways of doing wall-modelled LES, and one of them is called wall stress modeling, and this is what I'm going to focus on in this talk. And probably it's safe to say that that is pretty much the most widespread way of doing wall modeling. Now, for wall stress modeling, we're going to apply the same procedure at each time step and at each wall face of the simulation. Okay, this procedure is basically summarized in these 4 steps. The first step of the procedure is that we sample the solution of a LES from some point at a distance h from the wall. Okay, so let's look at this figure. So we have the LES domain here, this is the grid, this is our wall, and we're now looking at this wall face. So what we're going to do is we're going to go up a distance h from the wall, and from this point we're going to sample the solution to our Navier-Stokes equations. So it can be the velocity values, can be the pressure values. We can also compute some kind of derivative quantities, for instance the pressure gradient. Basically whatever we want to grab from our LES solution we can grab. And we're going to put that in this box called the wall model. And more about what is inside the box later, but what we're going to say now is that the job of the wall model is to predict the filtered wall shear stress. Okay, so what the wall model does, it gets the solution as the input and gives you the wall shear stress at this point as output. And when we get this output, the third step is to actually enforce this computed value at the center of a wall face. And there's also several ways one can try to approach this enforcing. One of it, and the one we are going to use here, is that you actually add some additional viscosity at the face in order to enforce the correct value of this quantity. Okay, so what's actually inside the wall model? What's inside the box? Now, again, there are several ways of doing this, but as you realize, all of the approaches are based on somehow connecting this sampled solution to the desired output, the wall shear stress, through some kind of equation. And basically, there are several levels of complexity here one can consider. The most complex wall models are based on partial differential equations. Then a little bit less complex are based on ODE, mathematically, based on ODE equations. And then finally, mathematically, the most simple ones are based on nonlinear algebraic equations. And that's what we're going to stick to here. So we're going to use an algebraic wall model based on so-called Spalding's law. Now, what is Spalding's law? Spalding's law, you can think of it as a wall function, or you can think of it as a law of the wall. So basically what it is a fit to the mean velocity profile inside a flat plate turbulent boundary layer. Now, if we look at this figure here, we have the mean velocity profile of a TBL in inner coordinates and plus scaling. And we have some DNS data to show the truth, so to speak. And then we can see that the Spalding law is basically a fit to the DNS data here, more or less. And that's not the only such law. There are many others. So, for instance, Reichhardt's law is another such law that provides a fit. Probably the most simple algebraic wall function is basically just the log law. And then you have only something which is valid here in this log law region. So what's good with both Spalding and Reichardt is that they're valid all the way from the wall. Okay, so this was obviously quite an intense intro. So as I said, if you want to read a little bit more about how wall modeling is done, my thesis I think is a good starting point, simply because there's lots of references inside there. So you can continue with other literature afterwards. But here I'll stop with that, and instead we're going to talk a little about what's the status in OpenFoam with wall modeling. And the way it is right now is that both the Foundation and the OpenCFD, and probably the Foam Extend versions of OpenFoam, they have some rudimentary wall modeling built in. So there are, I think, two algebraic wall models, one for smooth walls and one for rough walls. So the one for smooth walls is actually based on the Spalding law, which I introduced on the previous slide. It works fine. So you can go ahead and use it as a wall model. But unfortunately, that's the only thing that's there. So what we have been doing in the last 3-4 years is creating our own library for WallModelled LES in OpenFoam. And this is an open source library, so all of you can use it. And it contains a couple of algebraic and also ODE based wall models, so much more than what's in OpenFoam itself. Also, an important feature is that you can assign this h on a per face basis. So recall that h is this distance from which we sample our solution from the LES domain. So you can basically assign a different sampling height for each face, and we'll see that that's actually quite important. You can also control all the parameters of a wall model. So for instance, if we take the Spalding law again, you can see there's some model constants kappa and b here, so you can control the values of those. You can also control all the parameters, of the solver that's going to solve that nonlinear equation for you, for basically Newton iteration. Also, very importantly, it introduces a quite convenient framework for adding new models and testing out new ideas, hopefully. And recently we've released a new version of this library, so 0.40, and we didn't actually add any functionality in terms of wall modeling in this version, but very importantly we added the possibility to compile the library for pretty much all modern versions of OpenFoam from the foundation and OpenCFD. So before, the library only worked with version 3.01 of the foundation, but now we have a mechanism in place that allows the library to be compiled for any of these OpenFoam versions. So hopefully we can reach a much larger user base. Now currently it does not support Foam Extend, unfortunately, because I'm very unfamiliar with that fork of OpenFoam, and it's also, I think, quite conservative in its API, so quite a lot that has been changed in these versions has not been propagated to this one, and I personally don't use it, so I probably won't pursue supporting this fork unless I get a user. So unless somebody tells me, hey, really want to use your library with Foam Extend, could you please help me make a compile for Foam Extend, then I'll probably go ahead and try my best to support Foam Extend as well. Yeah, and as I said, it's open source, so I'll add a link to the library also in the description of the video, so you can go ahead and check out the source code. So during my PhD project, me and my colleagues looked quite extensively on how basically to make WallModelled LES work well. How do we set up the case so that it produces accurate results for us? And with the majority of those simulations we did were using structured hexahedrals, which is generally also what people mostly use nowadays with large eddy simulation in general, but also with WallModelled large eddy simulation. Based on those simulations, we could come up with quite concrete guidelines of what works well and what doesn't work well. And in particular, we have these 4 points I have on the slide here. And the first point is that you should use isotropic cells, and we recommend a density of about 27,000 cells per delta cube. So this means basically in one direction you have 30 cells across a length scale of delta. Now the second guideline actually refers to this H, and there the important thing is that you don't set H such that you sample from the wall adjacent cell. So it's totally fine to sample, for instance, from the second cell of the wall, but you should not sample from the wall adjacent cell. And here one should mention that, in the standard OpenFoam, exactly what is being done is sampling from the wall adjacent cell, and you have no way of controlling that. So something our library can do for you is that you can, as I said, set this H in a per phase basis. Now the third point is regarding subgrid scale modeling, and yeah, we haven't tested that many models, mostly focused on Smagorinsky, Whale, and also tried to use implicit LES. The conclusion is that the Whale model seems to be a good starting point. At least it's a good choice. It's not too diffusive, but it's diffusive enough to get the momentum redistribution in the boundary layer right, because without any SGS model, things actually don't work in WallModelled LES. We had very good experience with implicit LES with standard well-resolved RGD simulation in OpenFoam. So that's become our basically go-to approach. Turn off SGS modeling altogether. But with WallModelled LES it doesn't work, so you should use an SGS model, and the Whale is a good starting point. And the fourth one concerns the convective scheme, or the discretization scheme for the convective fluxes. What we recommend is using some mildly diffusive scheme. For instance, Lust is a good choice. This is again different from what we saw with well-resolved LES, where we typically used simply linear interpolation, which is unbounded, but nevertheless we could get very accurate, nice results without having any problems with oscillations. But with WallModelled LES, we actually saw that having some sort of diffusion coming from numerics or VSGS modeling is a very, very good idea to get accurate results. Now this, of course, this was a very dense summary of a whole bunch of simulations and studies, and if you want to look in more detail to how we arrived to these conclusions, again, my thesis is a pretty good starting point, I think. But the focus of this talk is how about unstructured meshes? So can we use them? Because we really want to use them so that we can, consider complex geometry flows, which are pretty much impossible to mesh with structured hexas. And if we can use them, so how should we mesh our boundary layer so that it's appropriate for WallModelled LES? What kind of cell type should we use? And also very important for us, so do all of those guidelines, those 4 points that we have here, do they actually still hold for simulations on unstructured grids? And so these 4 questions are basically the focus of this talk. So we have devised kind of a meshing strategy based on what we have seen for structured hexahedrals. And it's based on the following principles. So the mesh should be isotropic, just as we saw with hexahedrals. It's the best result. And then there's this question of how do you actually characterize, the cell size. There are different ways of doing it. One way of introducing a length scale is, for instance, the cubic root of the volume of the cell. But what we advocate for is that we actually consider the average distance between the cell centers, which we call D, and that's going to be the characteristic size of our cell. And the reason for that is basically because this D enters of discretization formulas. So from a numerical point of view, I think it's a very reasonable way to characterize the cell size. And the perhaps most important point is number 3, and that is that the resolution of the grid should stay constant with respect to the local thickness of the boundary layer. Now here in the bottom I have a surface mesh of a wall with for a flat plate turbulent boundary layer flow, and the boundary layer is going to grow in that direction. And then we see that since it grows, delta grows with x is this one, the characteristic size of a grid also grows then, because we keep d a constant fraction of delta. So as you can see, the mesh is more dense here in the beginning, then it becomes to be more and more coarse. What is interesting also is that if we want to fix h to a particular fraction of local delta as well, that means that our h is going to vary with x as well. So we actually need this capability that we have in our library, that we can set a particular value of h for each face. Now, if we look at how the characteristic size behaves for this particular mesh, we see that the fraction of the size of a plate in the spanwise direction with a characteristic size, it goes down, and if you look instead in plus units, it becomes larger and larger. Okay, so based on those principles, we devised a 4-step procedure on how to mesh the boundary layer. And the first step is you have to get an estimate of delta, because since the characteristic cell size is fixed as a fraction of delta, we have to know delta before we mesh. And for very simple flows, there are known estimates of delta. For instance, for a flat plate turbulent boundary layer, there is a power law estimate. But in general, what you can do is use a RANS precursor to that end. So you basically run a RANS simulation. It's very cheap in comparison to what you're going to do with a WallModelled LES anyway. And out of there, you can extract your delta. Now, the second step is that you mesh the wall surface. And that you do according to the principle that delta over d stays constant. Then the third step is that you take your surface mesh and you extrude layers from 0 to height delta, okay? And with the height of each layer, again, approximately d. So as a result of steps 2 and 3, you get a mesh which is isotropic and with a constant resolution with respect to delta, just as we want. And then of course the fourth step is that you basically mesh the rest of the domain. So here in the figure I have two examples for different cell topologies. So on the left we have a quad dominant surface mesh, and you see the layers. And here on the other side here we have polygonal cells, and then we extrude the prisms, and then we have some polygons here in the free stream region. And as you can see, the layers are extruded exactly to the estimated value of delta at this point. And these two meshes that I've just introduced were actually used by us to simulate a flat plate turbulent boundary layer up to a Reynolds number of Reynolds theta about 4,000. And these much more detailed accounts of these simulations you can find in this paper in the conference proceedings of the 7th European Conference on CFD. It was in Glasgow this year in June, and the full text is available on ResearchGate. So I'm going to add a link to the PDF also in the description of this video. And as I said, for a flat plate TBL, we can estimate delta using a power law quite accurately. And for the resolution, we had to opt for somewhat lower resolution than what we recommend generally. So delta over D is about 0.5 for these meshes. And as I said, ideally we would like to have 30, but then we would have such large meshes that we can't really afford running them on the machines we have. As I said, two meshes, paved and polyhedral, so paved is this quad dominant one. And the mesh sizes turn out to be a little bit different. So the paved one is 15.5 million and the polyhedral one is 12.9 million. So that actually tells us that, for different types of meshes, if you keep the D the same, the average distance between the cell centers, depending on the cell topology, you're going to end up with a different amount of cells for a given volume. So in this particular case, the polyhedral cells end up saving, how much is it? 2.5 million approximately. Just to compare, if we would instead opt for a wall-resolved LES and mesh the same geometry and aim for the same Reynolds number, what we would get is approximately 250 million cells. So as you can see, we save a lot of resources by opting for wall modeling instead. Okay, so let's look at some results. And I'm going to have four curves here, four results curves, and they correspond then to using the paved mesh, the orange curves, the polyhedral mesh, the blue curves. And then for each of them, we have two different simulations that we have conducted. And one simulation is that we sample from a wall adjacent cell. So that's what we have previously said you should not do. And then the second one is that we sample from the, third cell instead, which we expect will lead from a better result. And in terms of SGS modeling and the numerics, we use the whale model and the LES scheme, just like we recommended based on the simulations we've done using structured hexes. And here we have a result for the skin friction coefficient as a function of Reynolds number. We have some benchmark data, we have both DNS, and we also have a power law estimate. And what we can see is that basically on both meshes we get very nice results, and there's a systematic error introduced when we use this option. So when we sample from the wall adjacent cell, we get an underprediction of CF. And that is the reason why it's not recommended to use the wall adjacent cell for sampling. So this is something that has been seen both by us, but first before us, systematically across many different types of solvers based on different numerics and so on and so forth. So it basically is an established fact, I think, right now that sampling from a wall adjacent cell leads to the systematic error in CF we see here. But if we opt for sampling from the third cell, we get a very, very nice result for CF using both meshes, which is, of course, very good. Now, here we instead have mean velocity profiles, here in inner scaling, at 3 different downstream locations corresponding to these Reynolds numbers for which we have DNS data, shown in black here. And otherwise the legend is the same. So since we're looking here in inner scaling, we have the effect of the underprediction of the tau wall or CF that we saw in the previous slide. So basically when we sample from the first, from the wall adjacent cell, we have this systematic shift of a mean velocity profile in inner scaling upwards. This is also sometimes referred in the literature as the log layer mismatch. So basically the true log layer is here, but we are shifted in our results in comparison to the truth. But if we sample from the third cell, then we see that we get quite an accurate curve, perhaps a bit too pronounced of a log law compared to what is reality is for this quite low Reynolds number, but nevertheless quite good results. And that's all I'm going to say about the flat plate TBL. If you want more results, including the second order statistics of velocity, then you can check it out in the paper. Now, what I'm going to continue with here is present some results from a paper which is not written by me, actually. It's written by Livendahl and Johansson, and Matthias Livendahl is my supervisor for a PhD studies I recently finished. So he has kindly agreed to allow me to share these results. And in this paper, they have simulated the hull of a Japan bulk carrier, GBC for short, JBC, in model scale. And the Reynolds number is very high for this one, so it's an order of million, 10 to the power 6. What they focused on here is looking at the behavior of WallModelled LES in the boundary layer that we get on the hull of this ship. So they didn't look that much at the wake and things like that, but they focused on can we get an accurate solution for the hull TBL. And to provide a comparison, they also simulated the same flow with RAS using k-omega SSD, and that was also what they used to get the delta estimate that we need to create the mesh. And in this particular case, they've only created one grid, the polyhedral one. As we saw before, it leads to a less amount of cells for a given volume and a given characteristic distance between the cell centers. And in this simulation, they also sampled from the wall adjacent cells. So we can expect actually that there will be some underprediction in CF. We're going to see that. The mesh is nevertheless quite large. It's 137 million cells, so it's quite an ambitious simulation. Basically, the main idea with this simulation is, like a proof of concept that we can use the approach that we've developed in order to simulate, real life flows. So this is the ship hull. Very interesting to see what we'll get. And on this slide, we have again CF multiplied by 1,000 here. And this is, the distance along the hull. And then this is the section where the hull is basically parallel. And we can look at the side of the hull, or we can look at below the hull. And here we also use a power law estimate to get an idea of what the solution should be. What we can see is the RANS performs actually quite well for this flow, or for this region of the flow, I should say at least. And both below on the side we have something which is quite close to the power law estimate. Now for WallModelled LES, we again see this systematic error in CF, which we can say is due to the fact that we've used sampling from the wall adjacent cells in this simulation. But otherwise, the behavior, the behavior of a curve is very close to the RANS and to the estimate, but there's this systematic shift that we talked about before. Here on this plot, we look instead on the growth of the boundary layer, so in delta 95 in centimeters in particular, and the distance along the hull on the x-coordinate. And what we see here is that for RANS, the boundary layer grows faster, and for WallModelled LES it grows slower, and that is directly connected to the fact that we underpredict the wall shear stress in the WallModelled LES, meaning that we take away less momentum from the boundary layer than we should, which means that it grows slower. So that's the explanation behind this difference here. It's still explained by the same fact. Looking at the velocity profiles here along several downstream locations, we see pretty much that the profiles look quite similar for both the RANS and the WallModelled LES. And again, we see that for at a given station, the boundary layer that we get with the RANS, so that's the dotted one, right? Yeah, the dashed line is the RANS. So the dashed line is, the profile is thicker. So we can see that, for instance, here it's very clear that the profile we get from the WallModelled LES is closer to the wall. The thickness of the layer is smaller. That's exactly what we saw on this previous slide, basically. But the shape of the velocity profile is, on the other hand, very similar, and the WallModelled LES gives us a nice prediction. Okay, so time to conclude. So the main point of this talk is that we have introduced a strategy for unstructured mesh generation for WallModelled LES. It's a very concrete procedure that I think everyone can try and use. And to test it, first we constructed two meshes for a flat plate TBL, one pave and a polyhedral. And we saw that we can get accurate results using the same guidelines that we have developed for hexahedral meshes. And that's very important. So basically we see that what we have known transfers nicely to the case with unstructured meshes. We also looked at results for the Japan bulk carrier that were obtained by Mattias Levendal and Mattias Johansson. And basically it's a proof of concept that we can use the developed meshing strategy to apply it to real-life cases. We saw that the accuracy trends are pretty much the same as for the flat plate simulation. Unfortunately, they only did a simulation with sampling from a wall-adjacent cell, which we know that leads to suboptimal results. But nevertheless, we saw that we can use our approach to simulate real-life cases. Now, regarding future plans, we would like to continue the Japan bulk carrier simulations. In particular, the low-hanging fruit is try and use some other cell for sampling, like maybe the second consecutive cell instead of a wall-adjacent cell, to see how much our results improve. Hopefully, we can do some work there. Also, I've recently announced a master thesis project proposal at Chalmers, but we welcome students from other universities as well, in case you're interested. And that master thesis project is going to be on more systematically assessing the accuracy of WallModelled LES on different meshes. So, going to generate different meshes with different cell topology, dig into a bit more on what kind of mesh sizes for a given volume a given cell topology gives. Just basically look at a bit more detail in all of those things. Probably mainly looking at some simple flow like turbulent channel flow, maybe even applying it to something more complicated if time permits. Okay, so yeah, this brings me to the end of this talk. If you have any questions, you can of course write them in the comments, and I'll be happy to discuss this work with you. And I'm generally open for any type of collaborations or ideas on how one can develop this approach. Also, would be very glad if you try and pick up our library and try to use it. We made it open source and put quite a lot of effort into it, so hopefully it can come to some use for those that are interested in scale resolving simulations. Okay, thank you for now.